Alright, in this lesson 4.2 we're going to look at finding rational zeros of polynomials, but today we're going to focus on the factor theorem and also looking at, once we find roots, how those roots can help me find the zeros, which then allow me to write my polynomial into factored form, and considering the idea of multiplicity when I have repeated zero values. So these first couple slides are a lot of just FYI information. First of all, the factor theorem. Previous lesson we learned about the remainder theorem, and the remainder theorem said when I had polynomial set up with synthetic division, the last number within my synthetic division would be the remainder, and that the value of r, or the value I was testing, r, would generate that value of y that we get as the remainder. So it's the same thing as like saying p of 3 equals 16. If 3 was my number in synthetic division and I got a 16 as the remainder, those two became accordant. So the factor theorem kind of goes along with that. If I know that my remainder is a 0, then I know that I have found a factor of x minus r for my polynomial px. This is what's going to begin to help us take polynomials in expanded form and factor them so that I can graph them. And then the converse statement to that, if I know I have a factor of x minus r, then I know that r is a 0 of my polynomial. So now we're specifically looking for remainders of 0 for the factor theorem. So let's give a couple examples here. We've got x minus 3. We're going to show that that is a factor of the polynomial px equals x cubed minus 2x squared plus x minus 12. So if x minus 3 is indeed a factor, that must mean, again, this is the x minus r form, and we're going to be considering r values. If my remainder is 0, that r is going to be one of my zeros. And so we set this thing up with synthetic division. Here we are looking for a proof that f of 3 is indeed equal to 0. So here we are setting it up. Replacing, putting things in descending order, and then replacing any missing terms with 0. So we're all set. We discover that, yep, we get a remainder of 0. So that then therefore means that x minus 3 is indeed a 0. And we can begin to factor this polynomial. So in factored form so far, it would be x minus 3 times, now remember this is x squared plus x plus 4. So that could be the other factor. That could be my factored form so far. If we were to try and factor x squared plus x plus 4, we discover that that actually generates imaginary roots. All right, what about something where I've got a big gap? I've got a 25th power on my x and then all the way down to a constant. So I'm missing the 24th all the way down to the first power. I don't want to set up synthetic division for this. So this is where then we consider thinking about this setup of just direct substitution. If x plus 1 is supposed to be a factor, again, thinking of my x minus r is my factor. In this case, my r is equal to a negative 1. This, x minus a negative 1 is equal to x plus 1. That's what's telling us my r is equal to a negative 1. So what if we just directly plug it in with substitution? That's what's happening right here. We plug a negative 1 in there. Negative 1 to the 25th power is negative 1. And negative 1 plus 1 is equal to 0. So, yep. Piece of 1 equals 0. So x plus 1 is indeed a factor of that polynomial. All right, we like to see polynomials in the factored form like this. It's easy for us to find the zeros. And in this case, we're looking for the polynomial p of x equal 3 times quantity x minus 5, quantity x plus 2, quantity x minus 3 squared. So we have it set up so that if I'm looking for zeros, I can use zero product property. And zero product property states that x minus 5 must equal 0, and x plus 2 must equal 0, and x minus 3 squared must equal 0, but we just look at the binomial portion of that. So my zeros are x equal 5, negative 2, and 3 would be the zeros of that polynomial. What's the degree of the polynomial? Well, if I were to expand, so now we're working on this 2x, x minus 4x plus 1, x minus 7 squared. If I were to expand that, I would discover that this is a 1, 2, 3, 4, 5 fifth degree polynomial. How do we get that? Just looking at the factored form is we just look at the powers on the x's, x to the first. This is an x minus 4 to the first, x plus 1 to the first, x minus 7 squared. So I just simply add up my powers. 1 plus 1 plus 1 plus 2. So I have a power telling me I've got a fifth degree polynomial here. So when it's in factored form, just determine what the power is on each of those x's. All right, so what are the roots then of this polynomial x to the fourth minus 1? So here's one that I could set up synthetic division with, missing a 0 for the third term, for the third power, second power, and the first power. But I also could recognize that x to the fourth minus 1 is a difference of two squares. And if that's the case, then I can simply factor it. So you take the root of x to the fourth, which becomes x squared and x squared. The root of 1, which is 1 and 1. One of them's plus, one of them's minus. Now the x squared plus 1 binomial, we can't break that down any further. However, the x squared minus 1 is another difference of two squares. So we just drop the x squared plus 1 still. Then we take x and x, which are the roots of x squared, and once again, 1 and 1, roots of positive 1, or negative 1. One of them has to be negative, one of them has to be plus. And then since we're looking for roots, it means we're going to be set this thing equal to 0. And I get x is equal to plus or minus 1. And that comes from these two. And then I also get x squared plus 1 equals 0, or x equal plus or minus I. Let's look at that one for a second. X squared plus 1, set it equal to 0. X squared would equal negative 1. Take a square root, and we take a square root of a negative 1, we get a plus or minus I. Okay, now, what are the x intercepts of that polynomial? Well, the x intercepts are the real roots. So there's the important thing there. So we go back up and we look at up here, and there are our real roots. So our real roots are going to be plus or minus 1, are the x intercepts of this graph, and I pick the graph. So the factored form, again, helps me find the zeros. The zeros help me to graph. Let's try some more here. So x minus 1, you're going to probably want to pause right here if you want to try these on your own. Here's what you would have. Again, this is another one where x minus r, where r is equal to 1. I'm going to go ahead and plug 1 on a set synthetic division problem of that many zeros, and I get a 0. And so because of that, we're checked. X minus 1 is a factor because I had a remainder that was 0. On the next one, what are the zeros of this polynomial? Again, making this equal to 0. And then doing zero product property. I get my zeros are equal to a -3, a -7, a positive, and a -1. What are the roots of an x squared plus 4 equals 0? That is not a difference of 2 squares. So if I solve this one for x, I'm going to get x equal plus or minus square root of -4, which is plus or minus I root 4, which is plus or minus 2i. So here I get some imaginary roots. And because there are imaginary roots, there are no real solutions. That means there are no x intercepts for x squared plus 4 equaling 0. Multiplicity. This is how you determine what's going on around your x-intercepts with your graph. Multiplicity describes the number of times a factor, which is a 0, is repeated in a polynomial. So when we say repeated, we're meaning, like in this example, p of x equal x times x plus 2 cubed and x minus 4 fifth. Those are multiplicities. Multiplicity of 3 is called a triple root. And at some of these multiplicities, there are unique things that happen around the x-intercepts. We'll talk about that. All right, so we already looked at the previous problem, how you find degree of a polynomial with a bunch of factors. Remember, you add the powers of the x's. So we have x to the first power here, and then an x to the third, and then an x to the fifth. So this actually, degree-wise, would be a 9th degree polynomial. Now, in terms of multiplicity, we have zeros of 0, -2, and 4. -2 has a multiplicity of 3. It has a power of 3. 4 has a multiplicity of 5. Power of 5. So here's what we have. Now, we didn't talk about 0. 0, being a power of 1, has no multiplicity. Multiplicity means we're duplicating it, or we're producing it more than one time. So we have no reproduction if it has power of 1 there. All right, let's move on to the next one. What is the degree and multiplicity of each of these zeros? Again, multiplicity is saying how many times is it going to be repeated, and that will relate to the power. So our zeros, again, x plus 5 squared is a factor, x minus 1 is a factor, x minus 8 to the 4th is a factor. And so from the factors using zero product property, we would get that my x equal -5, 1, and 8 are all zeros. And then they have the following multiplicities. -5 has a multiplicity of 2. 8 has a multiplicity of 4, and 1, and once again, no multiplicity on that. number 5 example. Find p of x, state its degree if its zeros are 3 with a multiplicity of 2, and negative 2 with a multiplicity of 3. So let's clarify some things. What are our zeros? Our zeros are 3 and negative 2. What is our multiplicity? Multiplicity of 2, multiplicity of 3. So just from this information, we're going to write this of least degree. I'm trying to make it as small as possible power-wise. So maybe we start out with writing just what the zeros are going to be, but write them now as factors. So if one of my zeros is a 3, remember that this is an r. That would mean x minus 3 would be one of my factors. And once again, I have a negative 2. That's an r. And that would mean x minus a negative 2, or x plus 2 would be that factor. And then now we simply put the multiplicities together. So the 0, or the 3, had a multiplicity of 2, which means it gets a power of 2. The negative 2 had a multiplicity of 3, which means it gets a power of 3. And this would be our polynomial written in least degree form for that information that was stated. Now let's talk a little bit about these two special cases of multiplicity. The x minus 3 squared. This guy is called a double root. And the x plus 2 cubed is called a triple root. And now, what happens, what makes these unique? Well, on double roots, my graph will bounce off of that x-intercept. And on a triple root, my graph actually approaches the x-intercept, kind of flattens out, goes through the x-intercept, and then goes vertical or well, up or down, one of the two ways. So I'm going to just do a real quick sketch on the graph for this thing, for x minus 3 squared, x plus 2 cubed. Here we have negative 2, positive 3. What does it look like? Well, at the negative 2, which is a triple root, my graph is going to come and approach it. Now, this is a 5th degree function. In the previous lesson, we learned about odd degree functions with leading coefficients are positive. They start low, they end high. So this graph is going to start down on our left of negative 2. It's going to approach negative 2. And as it does, it's going to kind of flatten out as it gets near. It's going to kind of do this, and it's going to go through. And then somewhere along the way between negative 2 and 3, it's going to switch directions and head back down to our next x-intercept, which is a 3. So doing something like this. And as it comes to the 3, because it is a double root, every even root, my graph bounces off of that point. So my graph comes down and bounces off of that point and then goes back up. So this graph might look something like that. Triple roots, I flatten out at the x-intercept. Double roots, even roots, I will bounce off of them. So odd roots I go through, even roots I bounce off. All right, let's try these next two. We have a 0. Again, we'll highlight our zeros. Our zeros are 1 and 6. And our multiplicities are 5 and then no multiplicity, 6. All right, so we start with our factors. Again, once we know what our zeros are, I know I have x minus those values. So x minus 1 and x minus 6. Now we just put the powers in that is associated with our multiplicity. So 1 had a multiplicity of 5. And 6 has no multiplicity, which means I don't put anything there power-wise. And I end up with this. This is a 6th degree function. Thinking graphically, positive coefficient leading, it opens up, starts up and ends up, and then it goes through my x-intercepts at 1 and 6. It goes through both of them, doesn't bounce off of any of them. All right, what about this next one? Polynomial with a 0 at 0, at -1, and then we have these two, 5 minus I and 5 plus I. What are the respective multiplicities? Oh, I forgot one of the zeros. 2 is also a 0. 2 has a multiplicity of 2. -1 has a multiplicity of 3. 0, 5 minus I, 5 plus I have no multiplicity. Okay, so we just repeat our process again. Write everything. 0 as a factor. So x minus 0. I don't have to really, even though x minus 0 is technically correct, this really is just saying x. And then 2, x minus 2. And then 0 of -1, which is an x plus a 1. And then a 0 of 5 minus y. So I'm going to write it like this, x minus, and then in another bracket, or another set of parentheses, we have 5 minus I. And then we have an x minus, and then this time a 5 plus I. So again, all my r values go in after my x minus. All right, let's put the multiplicity numbers, the powers here. 0, no multiplicity. 2 has a multiplicity of 2. 1 has a multiplicity of 3. And then the x minus 5 minus I and the x minus 5 plus I, we're just going to leave them alone, like that. All right. Now, you might find that some people actually do with those imaginary zeros down there. Might write it like this. X, distributing that negative, x minus 5 plus I, and x minus 5 minus I. You might see it written that way as well. Or you have these real, so both of those right now are in a plus bi form. A plus bi, A plus bi, where actually x minus 5 is my real part, that's my A, and then the bi is just your I part. So x minus 5 are the real parts of those complex numbers there. All right. All right, let's take a graph now. Instead of being told what our zeros are and what their multiplicities are, let's see if we can interpret that information from the graph and then write a polynomial with a leading coefficient of 1 and assume all the zeros are integers and give the degree. All right. So we have a couple things to look at here. First, we want to look at the end behavior. What's going on the ends of the graph? So in this first graph, I have a graph starting down and ending up. And based on what we learned yesterday with end behavior, we know that if we have a graph that starts down and ends up, that we have an odd function with a leading coefficient that is positive. So we know we've got that going on. Odd function, power 3, power 5, some 7, something, and leading coefficient that's positive. So we can determine that just by looking at the ends. Then we go and we take a look at the x-intercepts. So I'm crossing at x equal -3, crossing at x equal 2, crossing at x equal 5. And because of that, those are my zeros. Those are my r values. I can write my factored form. and say that p of x must look something like this. X plus 3 and x minus 2 and x minus 5. And then before I'm done here, I'm going to go back and I'm going to check. I'm going to see if the graph went through each of those points of the x-axis or did it happen to bounce or flatten out. And it did neither of those. It didn't flatten out, it didn't bounce, it just went through it, which means we can assume I've got a polynomial that's set to look like this. Yes, we could expand it out if we wanted to, but we can leave it in factor form as well. That's called linear. We're leaving things in terms of linear factors. In the next graph, we notice, again, in behavior, starting down, ending up. It also will be odd where the lead coefficient is positive. But this one has a few unique things going on with its intercept. So it's drawn like it's looking at above the x-axis, but it's really not. So we have a 0 there and negative 3. We have 1 at 1. And it looks like, again, it's going below, but it's really not supposed to be. We're just hitting that x equal 4 and then bouncing off. So here I've got a couple bounce points. And remember, bounce means double root. We're bouncing off of the x-axis there. All right, so let's see. So far we know we've got that p of x would have to equal x plus 3 and an x minus a 1 and an x minus a 4. But because we're bouncing off of x plus 3 and x minus 4, we're going to have to remember to include these powers of 2. And now, I have my polynomial. So 5th degree, so it's an odd function, again, higher degree than the one on the left. Now it's bouncing off of those x-intercepts, so I have to remember to raise those to a power of 2. We're trying to write it as a least degree polynomial. It could have been a power of 4, but we're writing it as least degree, so we're going to just assume power of 2. And there we have it.